Good day, my name is Sabrina and we Group 19 will be presenting Topic 25, the heat or speed hypersonic scramjets. A hypersonic scramjet is an air-breathing engine designed to operate at Mach 5 and above. Unlike conventional engines, it has no moving parts. Air is compressed by shock waves, mixed with fuel and combusted while the airflow remains supersonic to produce thrust. However, flying at Mach 5 is extremely challenging due to intense heating, unstable airflow and the very short time available for combustion. That's why it's described as trying to light a match in a hurricane. The Mach concept here is that the Mach number describes the ratio of an aircraft's speed to the speed of sound, where m equals v over a, while a hypersonic flight is defined as m larger than or equal to 5. So overall, the engine shape, shock waves, heat, fuel cooling, and structure must work together perfectly because failure in one part can cause total engine failure. Now I'll pass this on to my next teammate. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AMIR bin ZARAWI. We are from Group 19. Have you ever wondered why normal jet engine fail at hypersonic speed around Mach 5 and above? The biggest problem is heat. When air enters the engine at very high speed, its temperature rises instantly. This temperature rise is explained by the equation T0 equal to T1 times 1 plus gamma minus 1 over 2 times Mach square. At Mach 5, this caused the air temperature to exceed 1100 degrees Celsius, which is far beyond what turbine material can handle. Turbojet engine use compressor and turbine, but this rotating part overheat and fail at high Mach number. Ramjet engine remove compressor, but they still slow the air down, which creates extreme heating and unstable combustion. Scramjet engine solve this problem. They have no rotating part and the air stays supersonic during combustion. This allows scramjet to survive extreme temperature and enable sustained hypersonic flight. Thank you.
Assalamualaikum everyone, my name is NABIL HAZIMI. Today I will be explaining why leading edge heating occurs in hypersonic vehicle and how material selection plays a crucial role in preventing failure. At hypersonic speeds, especially beyond Mach 5, vehicles experience extreme aerodynamic heating. This is mainly caused by stagnation temperature, where incoming air is rapidly compressed and slowed to nearly zero velocity at the nose of the vehicle. The kinetic energy of the air is converted into thermal energy, causing temperature to exceed 1500 degrees Celsius. Conventional metals such as aluminium and titanium are not suitable under these conditions. Aluminium melts at around 660 degrees Celsius, while titanium low strength and oxidize at high temperature, leading to possible nose and wing edge failure. To overcome this challenge, advanced high temperature material are required. Ceramic metallic composite can withstand with temperature above 1500 degrees Celsius while remaining lightweight and resistant to thermal shock. Carbon composite can survive temperature exceeding 2000 degrees Celsius and maintain strength under extreme heat, although they require oxidation protection. In conclusion, using this advanced material improves safety, reduce the risk of mission failure, extend material lifespan, and make hypersonic flight more reliable and sustainable.
Hi Doctor, I'm Nshi. Today I'll be presenting fuel act as coolant. At extreme speed like Mach 5, the edges of the wing can reach over 1000 degrees Celsius. That's hot enough to weaken metal structure and even crack them. Unfortunately, traditional cooling system simply cannot handle this temperature. So the question is, can fuel cool the aircraft before burning? The answer is yes. We use the fuel itself as a coolant. This is called regenerative cooling. So let's look how it works step by step. Firstly, cold fuel enters channels inside the aircraft skin. As it flows, it absorbs extreme heat, becoming hot fuel. Finally, this hot fuel enters the scramjet engine where it burns more efficiently. So the fuel isn't just powering the engine, it's protecting the aircraft from burning alive. Let's move toward the physics formula. This formula is a fundamental equation in thermodynamics used to calculate the rate of heat transfer to a moving fluid. In this case, it's fuel. It is a variation of the classic heat equation, Q equals to mc delta T, adapted for a continuous flow system. So this is especially used for a cooling system to calculate how much heat a fuel can carry away from an engine or component to keep it from overheating. So the key point is the fuel acts as the coolant and energy source, improving survival and efficiency of scramjet.
Assalamualaikum and hi doctor. My name is Muhammad IRSYAD bin NUSHI and I will explain shockwave and aircraft shape in hypersonic flight. A shockwave is a sudden compression of air that happens when an aircraft travels faster than the speed of sound. At hypersonic speed, which is Mach 5 and above, this shockwave becomes extremely strong, causing sharp increase in pressure, temperature, and aerodynamic force. A hypersonic aircraft are designed to ride on their own shockwave. The shockwave stay attached under the aircraft body, trapping high pressure air beneath it. This high pressure helps aircraft generate lift. This design is known as the wave rider concept. That is why hypersonic aircraft are long and sharp. A sharp nose controls the shockwave angle, reduce drag, and limit extreme heating. Blunt shapes causes detached shockwave which produce more heat and instability. Shockwave also help produce lift by increasing pressure under the aircraft. The pressure differences between the bottom and the top surface create lift at hypersonic speed. This design improves fuel efficiency, flight safety, and supports advanced transportation Space System, and National Defense Technology.
Assalamualaikum. I focus on AI knowledge mining and real hypersonic physics data. At Mesh 5, the stagnation temperature of air exceeds 1400 degrees Celsius, which explain why conventional material and engine fail. And in a scramjet, air enter the engine at supersonic speed, and so combustion must occur in milliseconds, making it highly unstable. Then, using AI, we analyze scramjet combustion physics, temperature limit, and oblique shock correlation. The oblique shock correlation shows how the aircraft nose angle control shock wave angle, which directly affect air compression, heating, and engine performance. By optimizing this parameter, AI help improve safety, reduce development costs, and accelerate national hypersonic airspace capability.